Okay, good evening to all. Let us begin today's interactive session for week 5. This is part of Foundation Engineering NPTEL course by Professor Kousik Deb from IIT Kharagpur. I am one of the teaching assistants, Kashyap Vasudevan. Okay, so let's begin today's session. It would be great if we could have an interaction. So, any interruptions or any clarifications will be welcome. Okay. So, before we begin, let's just have a small recap about last week. I hope you must have gone through the videos. If you have not, in the last week, the week 5 content was regarding. First of all, we talked about allowable bearing capacity, the definition of allowable bearing capacity. Basically, there are two things that we have to be concerned about. Uh, One being our shear strength. In other words, bearing capacity with respect to shear strength that we have been already discussing all these days with respect to our different bearing capacity theories, and those are like with respect to shear strength, right? And the other one is bearing capacity with respect to settlement. So both the values might be different. We have to choose the sorry we have to choose the minimum value, minimum of the these, because if one of them is like, say, we have 400 kPa for this thing and 200 kPa with respect to settlement, we cannot design with respect to 400, right? Because our settlement will not be satisfied. And in many cases, if you observe, in most of the cases, settlement will be governing our allowable bearing capacity. So we can only allow whichever is the minimum value among these two. So we saw last week also, like the week before, how to arrive at the settlement. So the point of about that was the definition of allowable bearing capacity lies in the fact that which of these parameters is governing. Generally, it could be settlement, because most of the cases sharing strength failure will happen only after a huge settlement. But for our serviceability condition, we cannot afford to have settlement beyond some values that we'll see in the coming slides. And after this, sir discussed about different correlations. So we had talked about SPT test, from which we will get n SPT number, n value, which can be corrected, and that corrected n value can be used for different correlations to arrive at our bearing capacity, or even settlement. We can come to bearing capacity. So there is these three methods were discussed: Peck-Hansen and Thornburg method, Meyerhoff's correlation, and Teng's correlation. All these three were discussed. Even a numerical, if I'm not wrong, a numerical was also solved on this. After that, permissible settlement. This was the settlement I was talking about. We need to know these values. These values are arrived at for different countries. It might be slightly here and there different. For IS code, they have specified certain settlements which can be allowed. So many a times our bearing capacity might be very high when we, as I told you before, when we are doing with respect to shear strength. But with respect to settlement, we'd have to check and see whether it is satisfying. If it is not, we'll have to redesign. So design was also dealt with this week. We talked about design of isolated footing, combined footing, and raft footing. There are only small differences here and there. All these three were discussed by sir. And at the end of the week, also, sir started solving a special scenario, special question which dealt with both eccentric and inclined loading. So In the 2 weeks before, I guess, when we started with bearing capacity, we were taking like conventional problems, but here he began solving problems which is where we have a load which is like both eccentric. So if this is the center line, it is both eccentric and inclined with the angle. So okay, so that was what happened last week. Uh, so I have prepared a few I'm prepared with a few questions, and let us see. Mm, so okay, so problem one. This problem deals with Skempton's bearing capacity equation. So it was not, even though I think it was discussed in second or third lecture, if I remember correctly, he had solved a similar problem based on this. Skempton's bearing capacity equation. It's only applicable for clay soils. So the basic equation is like we have net ultimate directly. Uh, Net ultimate bearing capacity expression is given as Cu NC. This is the direct equation for Skempton's, okay, sorry, Skempton's bearing capacity. So from the equation itself, it's quite evident that it's only applicable for clay soil. So you have basically Cu and NC. So okay, so what? Let us just define these terms properly. This Cu is nothing but our cohesion. But with respect to this question, we need to take a weighted average of cohesion within our influence zone. When I say cohesion, I mean under shear strength. Cohesion influence zone. Okay. So why I'm defining it in such a way that because we have a layered soil, so our influence zone might be in multiple layers with the different Cu values. So the particular Cu value that we are interested in should be in our influence zone. We'll come to that. The next term is NC, the bearing capacity factor for cohesion. This NC is specified as 5 of 1 plus zero point 0.2 B by L into 1 plus point df by 2. So this is for rectangular footing. Okay, so it's as simple as that. Only two terms are there. So let us see. In this question, we have a square footing of 3 into 3, which is at a depth of 1.5 meter. So since it is a square footing, I guess we can reduce it, right? We can simplify this NC equation as, since B and L are equal, I can directly write 5 into 1.2, right? 5 into 1.2 into 1 plus 0.2 df by B. This will be 6 into 1.2 df by B. Okay. So I have simplified for the square footing. Okay, so we have a layer. Let's just draw it to make it clear. Just We have a layer. First, from ground level, the depth of footing is given as 1.5, and we have three layers, right? Layer 1, 4 meter, 4 to 6, 6 to 10. So we have 0, 4, 6, and 10. We have Cu values 25, 35, 51, right? So 25 Cu equal to 25 kPa, 31 kPa and 55, right? 51. C equal to 51 kPa. I guess this is 35, right? Okay. So layer 1, layer 2, layer 3. Uh, okay, so let us see. This is 3 into 3. 3 into 3 meters square footing, and our load is given as 550 kilonewton. So okay, so it's very simple. First, what are we supposed to find? We are supposed to find, using Skempton's bearing capacity. We are supposed to find calculate the expected factor of safety against bearing. So against bearing means we have the uh, bearing capacity with respect to bearing, and we can also find the actual acting pressure right now. So if we find the ratio, we'll get the factor of safety, right? The capacity divided by the present load. So the net pressure acting right now, it's quite clear that oh, Q, sorry, Qn, the present pressure is nothing but 550 divided by 3 into 3, right? That is 61.11 kilometer per meter square. Having said that, we already have this thing, so we need to find Cu. So Cu is the weighted average, right? So what is the influence zone for uh, bearing capacity? If you remember, the influence zone is the width of the footing. So the depth which corresponds to the width. So this is 3 meter. Below the footing, I have to go 3 meter. That is a B value. So 1.5 plus 3 is actually 4.5, right? So this level will be 4.5 meter. That is 3 meter B. So this is the influence zone. So within this influence zone, what is the weighted average of the cohesion? So first 2.5 meter. So this can be split into 2.5 meter and zero point 0.5 meter, right? So first 2.5 meter is 25 kPa. Next 0.5 meter is 35 kPa. The next layer divided by the total length is 3 meter. So this is how you take the weighted average, right? So the weighted average value comes out to be, if I'm not wrong, 26.67 kPa. So this is the influence zone, 1B below. If you remember, for settlement we had taken 2B. That was only for settlement. So whatever is in between 2B, we have to consider. We had calculated settlement in the last week, if you remember. So the reason behind that 2B was, if you like, I think I had mentioned it. It was because of the Bosnisk equation. For Bosnisk equation, for we are just assuming the pressure bulb for 10% of the applied pressure. The 10% of the pressure bulb for 10% of the applied pressure will be 2B deep from the footing. So that's why we are taking 2B for the settlement. Here it is bearing capacity. That is because of our failure surface. Our elastic zone is assumed to be only, it will go only up to B. So we are taking that. So that's that. So Cu we have. What else do we need? NC, right? NC is equal to, if you like, if I'm not wrong, 6. Okay, 1 plus zero point 0.2 depth of footing, 1.5 divided by breadth. So NC is 6.6. This NC should not be greater than 9. If at all, if you get a value greater than 9, you have to take 9. So that's the thumb rule. So we have at the end QNU is equal to 26.67 CUNC, right? 6.6. This is 176.02 kPa. So our factor of safety is QNU, our capacity, by the present pressure. So 176.02 divided by 61.11. This turns out to be 2.8. So this is a direct question. Sorry, it doesn't have any unit. My bad. So 2.88. Do we have an option for that? Yeah, yeah. We have an option which is very near. So it's 2.8. Okay. Uh, this was quite straightforward. So in the next question, actually, we are extending this question with the same data. The next question says consider the data given in the previous problem. Estimate only consolidation settlement after applying all necessary corrections. Give depth correction factor. Okay, so here the deal is that we are supposed to find uh, consolidation settlement, and correction factors are given. Depth correction is given as 0.89. Pore water pressure is given as 0.7. We have pressure distribution. So this is quite the same as we had done before in the previous classes. We have different layers, so let us just write it down in a proper way so that this becomes easier. uh, so this is the ground level. Have they mentioned water table? Water table is at ground level. So uh, this is the groundwater table. Now okay, let me just write it whatever is required for us, right? So our cu value is for the layer 1. Okay, for here we did not want cu. We have initial void ratio value, coefficient of compression index value, and yeah, these things is not required now. Okay, density. So just for the clarification, E naught equal to zero point 0.8, Cc equal to 0.34, gamma sat equal to 17 kilonewton per meter cube. E is equal to, E is our modulus, 17,000 kPa. In layer 2, we have E naught equal to zero point 0.6, Cc equal to point, okay, so 0.3, gamma sat 18.2, E is equal to 21,000 kPa. Here layer 3 is equal to 0.55, Cc equal to 0.28, gamma sat equal to 19.7. I'm writing from the question itself, and E is equal to 32,000. Okay, so just observe these values. Here our initial void ratio is decreasing, right? So that is a generally expected trend is like that, because as we go deeper and deeper, the soil will be denser, stronger, more compact, right? So if you see, void ratio is decreasing, that shows lesser and lesser voids as we go deeper. Cc value is decreasing, that shows it is lesser and lesser compressible as we go below. Density is increasing, our modulus E value is also increasing as we are going deeper. This is not the thumb rule, but this is what we expect generally as we in our stratigraphy. Okay, so we have layer 1, layer 2, and everything. I told you before the this the influence zone, right? So we have 3 into 3, and this is 2 is to 1. So for layer 1, uh, we are interested from the level of the footing. So what are these values? 4 meter, 6 meter and 6 meter and 10 meter. So I'm interested at the middle point of the this layer, that is this is nothing but minus 1.5 meter. So here we have 2.5 meter, 2 meter, and yeah, so our influence zone for bearing capacity was 1b, that is this red line. But for settlement, it is 2b, right? 2b means here we have b value as 3, so 2b will be 6 meter. So from 1.5 meter to 6, from that we have to add, right? So it will be 7.5. So this layer here, right here, it will be 7.5 meter. Okay. So having said that, this will be 1.5. So we have all the layer depths. Now for each layer, we can find the settlement. When we talk about settlement, as we have to consider the middle of that particular layer we are interested in. That is this into marks. So those depth we have to be careful. We will be finding the overburden pressure at that particular point. That is because we are assuming that all these properties is uniform throughout this layer, and we are considering it as a single layer of these separate layers, and we'll take it as a three different settlements, and we can add it at the end. Okay. So the basic immediate settlement, we are not much concerned about immediate settlement here because it's a clay. So the predominantly most of the bigger chunk of the settlement will be contributed by our primary consolidation since it is a clay. But we in actual in exact calculation we need to consider all the three. If you remember, immediate settlement, primary consolidation settlement, as well as secondary consolidation. Okay? Immediate settlement, you know these terms in the last class we had discussed. This is the applied pressure, breadth, mu and E value. There are standard values. We are already have E value. Mu is a Poisson's ratio. There are standard Poisson's ratio values. IF is the influence factor. It's given in the code. For square center is 1.12 if you remember. At corner and average values also we have. But here in our question, we are dealing with only consolidation settlement. So let's move on to consolidation settlement. This is the equation for consolidation settlement. So we have CC value given in the question, that is coefficient of compression index. We have initial void ratio. We need to find overburden pressure, effective overburden pressure, and as well as the increase in overburden pressure. Rest everything we have. Depth of the layer also we have. So if we can find it for each layer and add it. Since we don't have a coefficient of volume compressibility, we cannot use this particular equation. Okay. So let's start finding for each layers that we have. We need to find pressures, right? Overburden pressures. So let us begin. Overburden pressure for layer 1. Let me write like this. Sigma 1 dash, sigma 2 dash, sigma 3 dash. So layer 1, for layer 1 we have 2.5 meter thickness. Its center point is at 1.5 plus 2.5 by 2, right? And our saturated is 17. We can take gamma W as 10. So our overburden pressure will be our submerged weight into depth. Depth was 1.5 plus 2.5 by 2 because we need the middle of the layer. So this turns out to be 19.25 kPa. Because H1 is equal to 2.5. Here H2 is equal to 2 meter, our density is 18.2, and yeah, so overburden pressure in the first layer. Okay, so the first layer of overburden pressure due to the first layer will be um, this complete layer, right? So the whole 4 meter, this whole 4 meter has to be considered for the first layer. Then we have to take the half. So uh, 17 minus 10, that is the first layer 1 is of 4 meter thickness, plus 18.2 minus 10 into our 2 meter layers middle of the 2 meter layer is 1 meter. So this will be uh, 36.2 kb. If you are doing, if at all you are doing parallelly, just correct me if I'm wrong. And layer 3, let's move on to layer 3. Layer 3 is 1.5 meter thick, and both the complete layers at the top we have to consider. So 17 minus 10 into 4, the layer 1, and layer 2 completely if we take uh, okay, so this layer was 2 meter, right? This layer is, this layer h3 is 1.5 meter. Okay, so this is 2 meter, plus our third layer is 19.7 minus 10. Everything is under groundwater table, that's why I'm subtracting it by 10, assuming gamma w is equal to 10, because I guess in the question it was given. uh, yeah, it's given as 10, so we'll take 10 only. um, Into what is has half of the thickness, right? So the half of this is 1.5 by 2, so 1.5 by 2, that is 58.95. Okay, so that's there. So we have sigma 1, sigma 2, sigma 3. Now we need the increase in pressure, right? So delta sigma 1 dash. Here the challenge is like we have to take this particular distance. So as you remember before, whatever depth we are going, we have to just add to the dimension, because since it is 2 is to 1, this will be, if this is z, this is also z by 2, here also it is z by 2. So overall we have to add z to the dimension. In the other direction also it happens, because in the direction perpendicular to the this screen also it is spreading in that fashion. So z we have to add. So here z is half of 2.5, so I can add so our load is same as the total load, but divided by 3 plus 2.5 by 2, that is 1.25, into 3 plus 1.25. This turns out to be 30.45. So sigma 2 dash. Similarly, what is the depth here involved? For sigma 2 it is uh, 2.5 plus 1, that is 3.5. So 3 plus 3.5 into 3 plus 3.5. This turns out to be 13.018. And the increase in pressure at the depth of next depth is this point. So 2.5, 2, that is 4.5. 4 point plus half of 1.5. 4.5 is plus half of 1.5 is 0.75. So it is 5.25, right? So 550 by 3 plus 5.25 plus 3 into 3 plus 5.25. This is uh, 8.0. Okay. So we have all the ingredients now. We have to just substitute and get the answer. So our settlement 1 will be equal to CCH, right? So CC is 0.34 for layer 1, H is 2.5 divided by 1 plus E naught. E naught is 0.8, and log of okay, sigma 1 19.25, 19.25 plus 30.45 divided by 19.25. So S1 turns out to be 194.5 mm. Okay, to be precise, the answer that we will get is 1945 meter, because our h that we have given is in meters. So whatever that unit is, we'll go to get. I'm just writing directly in mm, and the second layer is zero point 0.3, that is our CC value, into thickness is 2 meter divided by 1 plus 0.6 log of our 36.2 is the overburden pressure plus 13.018 divided by 36.24. This turns out to be 50.03 mm. So S3 is equal to 0.28, that is our CC, 1.5, that is our thickness, 1 plus 0.55 log of 58.95 plus 8.08 divided by 58.95. So see, as we are going, this turns out to be 7.8. Okay. As we are going deeper, the settlement is decreasing for obvious reasons. The soil is stronger, and uh, the the CC value is reducing. So all those reasons. Okay. So what is the total? The total, if you do, I think you get 259.64 mm. Okay, so we have found the total settlement, but in the question we are supposed to do corrections also. So depth correction they have given 0.85. Okay. Okay, so depth they have given 0.85. Pore water pressure correction factor also 0.7. Sometimes it may not be given directly. So let us take it, just first just substitute. Depth factor is 0.85, and our pore water pressure factor is 0.7. So we can directly reduce the reduced settlement or corrected settlement is equal to 259.64 into 0.85 into zero point 0.7. This turns out to be 151 point, sorry, 154.48. Okay, uh, we have an option 156. Okay, so having said that, what is the takeaway from this question is like, we have found a settlement, but is it okay? Like if you look at the code, you will come to know that this should not be greater than 75 mm for this particular condition. This condition is isolated footing in clay for square footing in clay, right? So the limit is 75. We'll see how the limit at the end we'll see. But so this thing is not satisfactory. This particular design is not satisfactory for this particular uh, so we can suggest to suffice settlement, we can suggest them to bring this down a little deeper. Either you can bring it down or you can increase the dimension of the footing in order to satisfy our settlement criteria. Okay. So here another question that arises, they have given it directly. So if you remember, in the last week we had solved a problem dealing with this depth factor. So just to check, since we already have this d by lb, we know d is 1.5 and l is 3 into 3 lb. We'll get 0.5. So if you check this uh, graph for L by B ratio 1 and this zero point 0.5, we'll get 0.85. This is 0.85, right? That's what they have given directly. So even if this is not given, we can find it. Even if the depth factor is not given, we can find it from this graph. This is IS graph from IS code. Second one is pore water pressure correction factor. For that, you will need if it is not given, you can take zero point 0.7, I guess. But if it is not given, if you have more details like Skempton's pore water pressure ratio, Skempton's pore pressure constant A, and and if you have this Skempton's, if you are familiar with this Skempton's constant, parameter. It's not a constant. It's called a pore pressure parameter. I'll write pore water pressure parameter. Okay. Two parameters are there, A and B. Out of that, if you have A, there is again there is a table in IS code from which you can get this correction factor for water pressure. Okay. So I guess, is there any other takeaway from this? Yeah. Uh, yeah, so we can understand like so either we can increase our dimension 3 into 3 thing, and or we can bring it down. If you, I think if you bring it down to this 4 meter, it will be very good, because if you observe this, we can see that first layer is contributing to most of the settlement. So if you are avoiding the first layer, we can have a very good advantage. That is also an option. So whatever changes you are doing, we will have to redo all this settlement and check whether it is getting satisfied. Okay. Moving on to the next question. Uh, Next question is actually very less to do, but let us see. Uh, okay. So the question is like, we have a isolated footing 4 into 4. Here they have given this corrected n value, the SPT value, and we are supposed to find the calculate. Okay, we are supposed to find the in order to find the in order to use the Teng's equation, what is the n value that you will adopt. So that is not actually a very good big question, but we'll extend it later. So as of now, what is the n value? That is a question. So we have the n value at different depths. We know that the dimension as well as the depth of the footing. So the depth of the footing is if it is okay 3.5 meter, and yeah, and our breadth is 4 into 4. So we know that for bearing capacity we have to take um, 1b, right? So from the footing we have to take 1b, that is 4 meter. So this is our influence zone for when we are talking about bearing capacity. So whatever is there in this range, whatever SPT value is there in this range, we have to take the average. So that is, this layer is minus 3.5 meter, this layer is minus 3.5 meter, and this layer will be minus 7.5 meter. So from 3.5 to 7.5, whatever value we have to take the average. So that will be uh, n average. Since already it's corrected, we need not worry about it. From 3.5, that is 24, plus 30 plus 35 plus 32 plus 41. We have 5 entries, so we'll divide by 5. We'll get 32.4, out of which we have to give the smaller value. So 32. So the answer is 32. But this question is a very small. Uh, so that is a thing. Okay. So anyway, since we have this question, we can extend it. Let us find the bearing capacity using tense equation. So bearing capacity for tense equation is given like this for strip footing and square footing, square and circular. So this is the equation we have to use here since we have square. Let us see this terms. So here n term we know, we already talked about it. We already have found it, 32. It should be the average of the within our influence zone. B we know the breadth, RW and RW dash. If you remember, we have used this somewhere in the last week. So RW and RW dash, you can find out there is a chart for that. DF is the depth of the footing. So everything we know. This is the average. RW and RW dash we have to find out, right? So let us find out. So this is I hope you remember this. This is the diagram that we use for finding RW and RW dash. Here, okay, before that, here this RW and RW dash is nothing but interpolation from 0.5 to 1. This is actually 1, this is a printing mistake. For our depth. So for RW, we have to check dw by df. So our df is this thing. Okay, we didn't talk about water table, right? Let us assume water table is at ground level. If water table is at ground level, our dw is 0. dw is 0, and df is, so dw by df will be 0, so it's 0.5. So rw will be 0.5, and d dash w by b, right? This d dash w by b, that represents the water table is below the footing, then only it is relevant. So for that also we can give it as 0. Oh, okay, my bad. Okay. Let us modify. So if it is at ground level, no, if it is at ground level, both will be 0.5. dw dash dw will be 0, and dw dash w will be also 0. So both rw and rw dash will be our least value, that will be 0.5. So let's just modify this as at ground level, sorry, at footing level. So what if the our groundwater table is at the footing? If it is at the footing, our dw is equal to 3.5, and d dash w is 0, because d dash w is the distance from the bottom of the footing. So it's 3.5. So if it is 3.5, and 3.5 dw by df will be 1, right? So for 1, our this will be 1. So rw will be 1, and r dash w, this is a 0, since d dash w is 0. So r w dash will be 0.5. Okay. So if that is the case, we have both the things. So if we just substitute it, qnu is equal to 1 by 3 32 square into 4 into zero point 0.5, this is our RW dash, is 0.5, plus 3 into 100 plus n square. Okay, so n square is 32. 32 square df. df is nothing but 3.5 into 1. Okay, let me just verify it. 32 square. Okay, so the value comes out to be 4616.67 kp. Okay, so we have the QNU. Then to get to QN, that allowable, not allowable, safe, we have to divide it by factor of safety, right? But the factor of safety generally that we can give is 2.5. So okay, so 2.5, if we divide it by this thing, so 4616 by 0.67 by 2.5. So this turns out to be 1846.67. So this is quite high. If you have seen enough values, this is quite high. So it's very strong. That bearing capacity is very high. Again, so that is the reason. So we have to check the settlement also. There, otherwise it won't make much sense. We cannot design just on this. So we'll check settlement also. In order to check settlement, we have to utilize this graph. This is there in IS code. So the idea is we have to find, so as I told, for settlement we have to take 2b. So 2b means 2b will be 8 meter. So 3.5 plus 8, that will be if this is 2b, this length will be 2.5 plus 8, that is 11.5, right? So I think 11.5 we have to take. So unfortunately in the data we only have filled 9.5. So these things we have to consider when we are taking the SPT value. Since I have just extended this question, so let us assume till 11.5 it is 52 itself. So let that data for 10.5 be 52 and 11.5 also be 52. So if that is the case, I will take the average. The average n value, if you add from 3.5 to 11.5, we will get 24 plus 30 plus 35 plus 32 plus 41 plus 48 plus 52 plus the last two I'm assuming it as 52 itself on a safer side by 9. There are 9 entries. This comes out to be 40.67. We can take it as 40. So n average is 40. So this is a very interesting graph because we are getting settlement directly from SPT value. So here we have width at the bottom, that is 4 meter for us. So from 4 meter, if you take 4 meter and our n value is 40, and for 40 you will get this particular, and this is in log scale. So if you check the log scale, this will be like 1 2 3 4 5 6 7 into 10 to the power minus 3, and the unit is meter per pressure. So this much meters for 1 kg 1 kg per centimeter square. So for each 1 kg per centimeter square they have given the settlement. So this 1 kg per centimeter cube is nothing but 100 kilonewton per meter square. Okay. Okay. So this is the so this is nothing but 7 mm. So but we'd have seen that actual settlement we have to divide it by water table correction. Actual settlement is that obtained settlement. So this is, so this w dash also, for this also they have given the figure, which is an interpolation between zero point 0.5 to 1. So and d by b, our d by b is nothing but uh, okay, so our d by b, our d is 0, right? So in our footing, our water table is at the base. So at the base it is 0, d is 0, so this particular value is 0. So here correspondingly it is, we have w dash as 0.5. So w dash equal to 0.5, so it is 7 by 0.5. This is nothing but 14 mm, right? Okay, so we have 14 mm for each 100 kPa. So how to get so let us see, we have let us say our allowable for footing in clay, let us say the allowable settlement is 50 mm, let us say. Why 50 mm and all, we'll see. But if you remember, there is a table he had extracted from this IS code. So for that we can take 50 mm for isolated footing. We'll come to that. There is a table, IS code in a detailed table is there. 50 mm. If 50 mm is the allowable settlement, what will be our allowable load, right? So 50 mm is the allowable, and for what we have is 14 mm for each 100 mm 100 kPa. So our allowable QS will be, because if you look at it, QS by 100 ratio should be equal to corresponding settlement, right? So that is the idea. So QS will be equal to 357.14 kPa. So just look at the difference, like uh, with using Teng's equation, what we had got is a very extremely high value, 1800, almost 6 times. But with respect to settlement, we have a very lower value. So that's why these things are important. Uh, so just to extend this, since this was at the footing, right? So this, the groundwater table was at the footing. uh, it had a very lesser impact. So just to have a better thing, let us assume that it is at 1 meter below, for just to, for your understanding, for so that we can cover more cases. So let us say it is 1 meter below footing. What if it is 1 meter below footing? What and all will change? uh, our rw and rw dash will change, right? So our new rw, our new dw is 4.5, and d dash w is 1. So dw by df is equal to 4.5 by 3. That is sorry, dw cannot go beyond for 3, right? So because see, look at the range. Here we have dw by df as 0 to 1, so it cannot be greater than 1. So if it all it is greater than 1, we have to take it as 1. So though this is 1.5, right, we have to take it as 1. So our rw will be 1 only, but rw dash, dw dash by b is 4, right? So 1 by 4 is 0.25. So for 0.25, if I draw a line, I guess if I'm drawing a line for 0.25, you can interpolate also. Just by interpolation you will get rw dash as 0.625. because it's changing from point 0.5 to 1, right? Okay, so rewriting that Teng's equation, you will get what QNU is equal to 32 square into 4 into RW. First one is RW dash, right? So RW dash means 0.625 plus, there is a 1 by 3 if I'm not wrong. 3 into 100 plus 32 square, df df is 1.5 into rw is 1. So this time, uh, like, can you predict? See, here we have lowered the water table, so it has to be safer. If it is safer, our capacity is higher, so the condition is better, right? So capacity should be higher, and obviously from point 0.5 to rw, initially we had used point 0.5 rw dash, now it is 0.625, so the value will obviously increase. But still, just for the sake of our practice, let us multiply, and we will get 100, something like 2400 kPa. So since last time what we had got is okay, I have done some mistake. Okay, okay, here I had made a mistake. Instead of depth of footing is 3.5. Okay, sorry, depth of footing is 3.5. So kPa. So our net is this divided by 2.5. You can take 3 also as factor of safety, but anyway, so just for the sake of the argument, I am taking. I think I have made a calculation mistake, but anyway, I hope you got the point. So just give me a minute to figure out where I went wrong. 32 square into 4 into the, okay, this is correct, and this one, uh, yeah, so this value is wrong. So the final value will be 4787. I apologize, this is a calculation mistake, divided by 4787 divided by 2.5. Okay, now it is fine. So 4787.33 divided by 2.5 is 994. Okay, so it has increased, right? So when we lowered the water table, the value of our bearing capacity has increased. But however, we know that it's not governing our design, so we'll have to check the settlement just like before. So if we just we can use the same n average. The only thing that will change here is our w dash. Our w dash will be for d by b is now 1 by 4, right? So 0.25. So for 0.25, our W dash will be 0.625. Am I right? Okay, 0.625. So if you interpolate, you'll get W dash. So our new settlement will be 7 by corrected actual, 7 by actual settlement. Let me write this properly. For water table 1 meter below foundation level, my W dash is 0.625. So our actual settlement is equal to 7 by 0.625. That will be 11.2 mm. So for 11.2 mm, if you do the same thing here, QS will be assuming a 50 mm thing, 11.2 into 100, you will get 442.42 kp. Okay, so that has also increased since our water after when we lowered the water table, our bearing capacity with respect to settlement has also increased. However, it's very low when we compare to the with respect to bearing capacity. So it's quite clear that settlement is governing in this case. So generally, people with experience say that it will always most of the cases settlement will govern our capacity. So we'll have to choose this particular value. If at all this is not satisfactory, we'll have to redesign. Okay, so that's the thing. I hope you go through those problem solved by sir also. He has taken different cases. Uh, I also have tried to cover like other scenarios also. So just to wind up, let us wind up with a small question. So this question is the thing. So okay. So the question is like we have a center of two columns we have. So if we have two columns and its center to center distance is 7.5, so this is 7.5, and isolated on hard clay, isolated footing is RCC. All these points are relevant because I'll come to it. We are supposed to find maximum differential settlement. Okay, so the thing is like in IS code, this is a settlement thing I was talking about. IS code has given different settlement values which is allowable. So I would really recommend you to go through this figure, not to memorize this, but just at least have an idea because here, okay, let us see what all are given here. For different types of structures, steel structure, reinforced structure, that's why RCC I was talking about, reinforced structure, multi-story structure, and for different cases, isolated footing, raft footing, and for different types of soil, hard clay, plastic clay, they have given different values. What are the values they have given? Maximum settlement possible, differential settlement possible, and angular distortion. So we need to keep this in check because this is more important because as I told you, this will be governing our bearing capacity, allowable bearing capacity. So in the previous thing, plastic clay case for RCC I had taken, if you remember, 75 mm, and in the just previous problem I had taken 50 mm. That is because it is hard clay they had mentioned. That's why I had taken 50 mm. This is for raft. Okay, for raft footing. Uh, sorry, so not raft footing. The previous was not raft footing. It was plastic clay. Okay, first question. So the point is you have to check these things and check the correct. So differential settlement also they have given for RCC. It's 0.0015 length. So angular allowable differential settlement will be okay. Uh, allowable settlement. Allowable settlement is equal to 0.0015 into L. L is given as 7.5. So if I want my answer in millimeter, I'll write 7500 mm. So 7500 into 0.01, this will be 11.25. So we will get the answer directly. This is just a light. That's why I thought of discussing this because just because of this table. I recommend you to go through this table. This is there in our IS code 1904. Uh, so all the available things are given. Um, the condensed form of the only the required values are our instructor has consolidated, and in the slide, one of the slides he has shown. This is the actual diagram, actual table. Okay, so I guess we can conclude it now. Like again, if you have any doubts, just please share. If you are hesitant, please type it on your in the comment box or anything. You can also anytime you can put it in discussion forum. And one more thing I would like to mention is like if the questions are not satisfactory, if you want a particular case, or if you're interested to uh, do all do some other problem, just post it in the discussion forum. We are regularly going through the forum. If any queries are there, if you have any suggestions, uh, please convey through either by discussion forum or during the session. Thank you for joining, everyone. The next one will be on 3rd September, the coming Saturday, by Shiv Shankar Nandi, and the next Monday I will be taking. So for week 6. So thank you for joining, everyone. Again, have a nice day. See you in the next week.